Okay, today we are starting logarithms, specifically just the functions and their graphs. We're going to be doing a lot more with logarithms, but today we are just easing into what they are and looking at their graphs. So you are going to need a calculator handy, so make sure you have that. So what is a logarithm? A logarithm is the inverse function for an exponential. So when we have our exponential function, a to a power equals x, we write that in logarithmic form as log base a, your number that's being raised to a power, of your answer equals your exponent. It is another way to represent your exponent is equal to log of your base of your answer. So we can go back and forth from exponent form to log form. And we are going to practice first going from log to exponent form. So the easiest way to proceed with these types of problems is to identify each piece first. In this first part A on example 1, I've got log base 4. 4 would be our A of 256, that is x, equals 4, that is y. So putting all of these pieces into our exponential form, that would be that 256 is equal to 4 to the 4th power. Now these are pretty easy to check to make sure you've done them correctly because you should be writing a truthful mathematical sentence in the end here. 4 to the 4th power does in fact equal 256, so I've done this correctly. On to example B, log base 4, that is our A again, of 1 over 16, that is x, equals negative 2, that's y. So 4 to the negative 2 power equals 1 over 16. That is an accurate mathematical sentence, so I have done this correctly. Log base 36 of 6 equals 1/2. So 1/2 is equal to, excuse me, already making that backwards. 6 is equal to 36 to the 1/2 power. And again, if I had continued on and done this incorrectly, I would figure that out by checking the validity of the statement I have written. All right, so that's going from log form to exponential form. What about the other way around? So I'm going to rewrite the log form over to the side just so we have it handy. And we are going to identify each part in our exponential form. So 3 to the negative 2 power equals 1/9. 3 is our base A, y is our exponent negative 2, x is our answer, 1/9. So log base 3 of 1/9 equals negative 2. On to B. 5 to the 4th power equals 625. 5 is my base, 4 is my exponent, x is my result. So log base 5 of 625 is 4. And lastly, 25 to the negative 1/2 power equals 1 over 5. My base is 25. Y is my exponent. X is my result. So log base 25 of 1/5 equals negative 1/2. All right, so that is practice going both ways from logarithmic to exponential and now exponential to logarithmic form. So the next thing we do with these logs before we go into graphing is evaluating the logs. We're finding what goes on the other side of that equal sign. And you do that by rewriting it as an exponent and solving. So remember, 3 is our base here. And what's on the other side of your equal sign is going to be your exponent. So 3 to what power is 27? Well, that's 3 to the 3rd power. So log base 3 of 27 is 3. Okay. Log base 2 of 2. So 2 to some power equals 2. Well, that would be 2 to the 1st power. So log base 2 of 2 is 1. Log base 36 of 6. 36 to some exponent equals 6. Well, that would be the 1/2 power, or square root. Log base 10 of something equals log base 10 of 1 over 100, that would be negative 2 because 10 to the negative 2 power is what gives you 1 over 100. Log base 2 of negative 1, so 2 to some exponent equals negative 1. That is not possible. There is no exponent that we would raise 2 up to that would give us a negative answer. Our sign of 2 is not going to change no matter what exponent we're raising it to. So this is not possible. All right. Now, just some other quick properties. So log base of anything of 1 is equal to 0 because you have to think about what that means. Anything to the 0 power is 1. A log base of itself is going to be 1 because anything raised to the first power is itself. And so that same concept kind of carries through. If you have log base a of a raised to an exponent, you're looking for that exponent. That is what the log is telling us. So common base for logs is 10. When we do not have a base given, we're assuming it's 10. Kind of like when we have a square root and we don't have a number written outside the radical, we assume it's a square root. So when you're not given a base, you assume it's 10, and that's actually the base that your calculator uses. Yes, you do have a log button on your calculator, and it is right here below the x squared. So if I want to find log, there's not a base written here, so we're assuming it's 10. Log base 5 in our calculator, we can just type it in. Again, we want to make sure we're closing the parentheses for us, so that would be 0.699. And we could do the same thing to find the log of 2.7. And again, rounding to 3 decimal places, that would be 0.431. Now, what if I need to use my calculator to find the log of something that has a base other than 10? We use this change of base formula. So if I'm taking the log of a base other than 10 of a number, I can find that in the calculator by taking log base 10 of the number divided by log base 10 of the base we're looking for. That is how we change our base. So here on example 5, part A, I'm looking for log base 8 of 132. So I'm going to take log base 10 of 132 divided by log base 10 of 8. And I'm going to put that into my calculator just like that. So I'm my log button, because that is using base 10 of 132 divided by log of 8. And that gives me 2.348. I can do this again here on part B. I'm looking for log base 12 of 0.6. So I'm going to take log base 10 of 0.6 divided by log base 10 of 12, and I can put that straight into my calculator. Log of 0.6 divided by log of 12, and we get negative 0.206. All right, on to the next topic with logs that we're going to focus on today, and that is graphing. So remember, we've been looking at exponential functions, so like 2 to the x power, and if I put this in my calculator and fill in that table, these are the values that we've been looking at previously. And so what that graph looks like is something like this. So that is our exponential 2 to the x power. And if you recall the features of that graph, our domain is all real numbers, our range is all positive numbers, we have a y-intercept at 0, 1, it's an increasing function, and we have a horizontal asymptote at y equals 0. Okay. Now, if I want to look at the graph and compare for log base 2 of x, because remember this is the inverse function, again, I can put this in my calculator, but my base is not 10, so what we're going to have to put in our calculator is actually that change of base formula. And we're going to have to do log base 10 of x over log base 10 of 2. That's what we're going to put into our y equals. So log of x divided by log of 2. And I'm going to go to my table. Well, there's the graph already, but if you go to your table, we are going to put in those values and fill in. Now, paying close attention, these x values that we have used are different from the values we used for the exponential function. And so our graph is going to look a little different. And what's actually happening here is these x values are going to get really close to 0 but never touch. And the reason that is because you have to think about what this means. We're talking about values of x y is our exponent. So 2 raised to the y power gives us x. There is no exponent that I can raise 2 up to that would give me a negative x value. So these need to be all positive numbers in our domain now. So our domain is only positive numbers, but our range is now all real numbers. My exponent can be any number. We now have an x-intercept at 1, 0. It's still an increasing function, and we now have a vertical asymptote at x equals 0. So that is what changes between the exponential and logarithmic functions. Now, of course, we are going to include some info about transformations. So starting here on number 1, I'm going to just put in that parent function that we just looked at together for log base 2 of x. So we just looked at this together. This is our parent function, so we're not going to have any transformations. We already said that our domain is all positive numbers. Our range is all real numbers. We are increasing. We do not have a y-intercept, and we do not have a horizontal asymptote. Okay, now looking on at number 2, the transformation that's going to be occurring here based on this equation we're given is that we are going to be shifting down 3. So I'm going to take these 3 points from my parent function and just shift them down 3. And so there is my transformed graph. This has not changed my domain or my range. It's still increasing. We still don't have a y-intercept or a horizontal asymptote. All that's changed is what my graph looks like. It is slumped down 3 units. All right, on to number 3. That negative on the outside tells me that this transformation is going to be a flip across the x-axis. So I'm going to go ahead and just have B through F written down here. But graphing-wise, again, I'm going to take those 3 points from my parent function. So starting with 1, 0. That is going to stay in its place because it's on the x-axis. My other point for my parent function was 2, 1. So flipping that across the x-axis, it goes to 2, -1. And then I had the point 4, 2. So flipping it across the x-axis puts it at 4, -2. So reflecting it across that axis is going to give me a picture that looks something like this. Okay. So this has not changed my domain. It's still positive numbers. My range is still all real numbers. What has changed, though, is that my function is now decreasing. And I still don't have a y-intercept or a horizontal asymptote. Okay, last one for this part, number 4. I've got 2 transformations happening here. We are shifting up 3 and left 2. So we're going to take those 3 points from our parent graph, and I'm going to shift them up 3 and left 2. And we're going to shift up 3 and left 2. And up 3 and left 2. So here's what my new function is going to look like. So my domain has changed. Because it shifted left 2, my new boundary is at x equals -2. So my domain is now from -2 to positive infinity. My range stayed the same. It's still an increasing function. I do now have a y-intercept at 0, 4. Oops. Didn't quite get that in line with the E. 0, 4. And I still don't have a horizontal asymptote, but I do now have a vertical asymptote when x is equal to -2. All right, then really quick, I want to touch on the natural log function, and I'm going to go ahead and fill in this information really quickly. So remember, our logarithmic base can be any real number, and when our base is e, we use the abbreviation for ln, which is log natural or natural log. So you actually do have this button on your calculator. Right below the log button, you have the ln feature. So this takes a log with base of e. And if we look at the graphs, it behaves the same way our other exponential versus logarithmic graphs do. Here we have our exponential and we have our logarithmic graphs. All of these features in the table below are the same as they were for our exponential and log functions with different bases. And that wraps up our first day of notes on log functions.